Hello, everyone. My name is Beatriz Ribeiro Vieira. It's a pleasure to present our work at the 11th workshop in Biosystems Engineering of the Biosystems Engineering Postgraduate Program. I'm a master's student in this program, and this work is titled Forecasting Amazon Deforestation, a high-resolution risk map for policy and climate finance. Our agenda today is divided into four parts. We will begin with the context, where I will discuss the challenges of the REDD plus mechanism and the baselines. Next, I will detail the methodology focusing on our random forest model. I will then present the results, where we will analyze not only the model's performance, but also a significant evolution in the drivers of deforestation. Finally, we will discuss the 24 risk map and its strategic applications. This work was co-authored by Márcio Souza da Rosa Filho, my partner while dealing with the algorithm, and Cláudia Belmonte de Ataíde Bor, my advisor in the master's program. Let's begin then by understanding the central problem that motivated this research. The REDD plus mechanism is a central strategy for climate mitigation. However, as authors like Angelson and Wonder pointed out, its credibility depends entirely on the scientific rigor of its methodologies. Following the Paris Agreement, the REDD plus has evolved from isolated projects to jurisdictional approaches integrated with national climate goals. This has intensified the need to define a robust and transparent baseline. The greatest methodological challenge lies precisely here, defining this baseline, which is the counterfactual scenario that estimates emissions in the absence of any intervention. The problem is that the traditional approach, which applies a baseline in an aggregated manner, that is a single average for the entire region, is fundamentally flawed. It ignores what Fernside and Lapolla have extensively documented, the spatial heterogeneity of pressure drivers, infrastructure expansion, degradation, and edge effects create highly localized deforestation fronts, making the actual risk completely different from one part of the Amazon to another. This image illustrates the point. On the left, the homogeneous approach treats the entire territory as if had one average uniform risk. On the right, we see the reality. The risk is heterogeneous, concentrated in pressure hotspots, usually associated with development and occupation corridors. To overcome this limitation, spatial risk modeling emerges as a crucial methodological solution, something that authors like Fernside and Freund also advocate for. It allows us to identify and, more importantly, quantify the areas under the greatest threat. More sophisticated nested REDD plus methodologies, such as the baseline allocation for assessed risks approach proposed by Freund and colleagues, depend precisely on risk maps like ours. These maps allow for a more equitable and effective allocation of the jurisdictional baseline, directing incentives to where the threat is real and imminent. Therefore, the objective of our work was to develop and evaluate a high-resolution deforestation risk map to serve as this essential technical tool. So let's look now at how we built this map. Our study area covers the 5 million square kilometers of the Brazilian legal Amazon. The variable we wanted to predict or target variable was the annual deforestation detected by ENPE's PRODIS system. The predictor variables or drivers, we use exclusively public geospatial data from sources like ENPE, MMA, and Map Biomas. The selection of these drivers were based on literature such as Lapolla's work on degradation vectors. We processed variables like Euclidean distance to roads from the DN19 and mining concessions from the ANM and rural settlements from INCRA. in addition to data on protected areas and land cover. The chosen algorithm was random forest, as studies by authors like Rodrigues Galeano and Saha demonstrate. The random forest is recognized for its high robustness and its non-parametric nature, which makes it ideal for handling the complex nonlinear relationships found in geospatial data. To ensure rigor, our work was divided into two phases. Phase one was historical validation. We used data from 2007 to 2012 to predict the observed deforestation in 2013, thus validating the model's predictive capability. And in phase two was the contemporary model. Once we validated the historical model, we trained the model with the most recent decade from 2013 to 2023 to generate the risk map for 2024 and subsequent years. The final output is a continuous probability map, which was classified into 6 risk categories for practical applications such as null risk, very low risk, medium risk, high risk, and very high risk. This flowchart summarizes our process. In phase one, we validated a model and achieved an area under the curve of 0.9795. The area under the curve is a metric that measures models' ability to distinguish between classes. A value this close to 1.0, as Congalton discusses in his work on accuracy, indicates an excellent performance. And in phase two, the final contemporary model achieved even superior performance with an area under the curve of 0.9829, generating the 24 risk map. So moving on now to the main results and what they tell us. The model demonstrated exceptional performance. The contemporary model achieved an overall accuracy of 96.91% and an area under the curve of 0.9829. These values indicate a remarkable ability to correctly predict where the deforestation will occur and where the forest will remain intact. It's important to note that, as we highlighted in the abstract, that this level of accuracy was achieved over a vast area of approximately 5 million square kilometers, attesting our approach scalability and robustness for jurisdictional level analysis. Perhaps the most critical finding of our study is the structural evolution of pressure drivers over the last decade. In the 2007 to 2012 period, the main drivers were, in order of distance, rural settlements with an importance of a score of 0.174, railways with an importance of 0.161, and mining with 0.154. In the more recent period, from 2013 to 2023, the relative importance of distance to rural settlements increased substantially to 0.213, indicating an acceleration of land occupation, and crucially, mining surpassed railways in importance, becoming the second most relevant driver. This is not just a statistical shift, it signals a structural change in the economic drivers of deforestation, possibly reflecting changes in public policies and commodity prices. These charts clearly show this change. Compare the chart on the left for the older period with the chart on the right for the recent period. We can notice how the bar from distancia assentamentos, which is distance to settlements, grows, and how distancia processos minerários, which is distance to mining, moves up to the second position, surpassing distancia ferrovias, which is the distance to railways. The final map translates these dynamics. The risk hotspots, the most critical areas, which are concentrated along the traditional arc of deforestation, but also in new emerging fronts like the south of Amazonas states. At the same time, the map reaffirms what studies like Barbara and colleagues have shown, The strong protective effect of indigenous lands in conservation units, they clearly appear as islands of low internal risk or null risk. However, the pressure on the perimeters is extremely high, reflecting the continuous external threat from drivers like land grabbing and illegal resource extraction. And here's our final product, the 2024 risk map. The areas in red and orange represent very high and high risk. You can see how they trace the arc of deforestation and the new expansion fronts. And notice the large light colored areas or white areas, which are precisely the protected territories, acting as crucial barriers against these advances. So now let's conclude discussing the practical applications and the conclusions of our study. The first application is direct and it's a strategic enforcement. This map is not just an academical exercise. It has significant actionable value. It allows governments, agencies to allocate their limited resources preventively and strategically instead of reacting to deforestation that has already occurred. They can optimize the use of financial and human capital to intervene in risk hotspots before the forest is clear. The second application brings us back to our starting point, the integrity of climate finance. Our map quantifies the heterogeneity of risk and in doing so exposes the inadequacy of homogeneous baselines. Applying an average deforestation rate to all areas results in two serious inefficiencies. Low risk areas are overcompensated, which diminishes the additionality of the investment. In other words, paying for something that would have happened anyway. Conservatively, the high risk areas, those that need it the most, receive insufficient incentives to compete with local economic pressures. Our map, therefore, provides the empirical basis for implementing methodologies like the baseline allocation for assessed risk, ensuring that payments for ecosystem service are channeled to areas under genuine and imminent threat, thereby strengthening the environmental integrity of the entire mechanism. In conclusion, first, the random forest model demonstrated very high performance in modeling large-scale deforestation risk for the illegal Amazon. Second, we confirmed structural evolution in deforestation drivers, highlighting the intensification of pressure from settlements and the advance of mining. Third, the 2024 risk map is an essential predictive tool for guiding conservation efforts more efficiently and equitably. And fundamentally, the map spatially defines the counterfactual scenario, that is, where deforestation is imminent. And as far as for our next steps, this map will serve as a foundation for the next phase of this research, which is the proportional and spatial allocation of the jurisdictional baseline, using the baseline allocation for assessed risk methodology, using the Brazilian FREL, which is the most recent one from 2023. And this is And thank you very much for your attention. And here's our contact information for any questions or future collaborations, and some of our references.